Hi there! Today we will be discussing how to connect your LED strip to your 12 volt power supply, and so you can get the best bang for your buck, and so it will shine as brightly as it should, even though this one is a very cheap replacement. And I have to say, never use a digital camera for recording anything, because I connected my one with mini HDMI. That's the only device I know that uses this one. With this one I wanted to connect to my monitor and to the DVI input, so that's basically the same signaling as HDMI, and well, it was all fine. I mean, I could see the preview, but once I hit the record, black screen. So that's really great. Now I am using a mirror, and well, let's get back to the topic. And okay, so it's really hard to be an idiot, and I've originally thought that I would get my AC from the wall socket, and I have my power supply, 12 volts, and then magically I will have right here a DC and connect it to my LED strip, right? Because I mean, obviously, without any issues, 12 volts, perfect. But the power supplies have usually a screw to adjust the voltage output, and this is really important. And let me tell you why this is the way it is. And I had here 4-meter cable to my LED strip, and lo and behold, I measured at the end of the cable, and it was not right. I measured here, it was 12 volts, and here I didn't have it. And well, the first problem here is a voltage drop on the cable itself. And what you have to consider, what I didn't, you have 4 meters in the length, but the electrons go one way and back, so in total 8 meters, right? So, and this is why we have to count. You can measure this and extrapolate from the measurements and do your best, but if you count this, you will be certain that you didn't mess up any leads or didn't make a poor connection. So this formula comes to help. And well, this exact formula is only for counting the percentage of voltage drop on the wire, and the norm, at least in Europe, is that in any kind of manufacturing and industry applications you cannot have more than 5% drop, and you have adjust the cable diameter to compensate for that. So let's just use this formula really quick. I will be going over each value, and we will be discussing what it means. Delta U, this is what we are actually looking for. So it's delta U and divided by, and UN, that's the, or on the western side, it should be VN. That will be our 12 volts equals 2 times and IN. This is the current. So for my example, I had 5 meters of LEDs, and for 1 meter it took 9.6 watts. That what was on the packaging. So for 5 meters it's 28 watts. So the current for this is 48 divided by 12, you have 4 amps. So you put here 4. We'll omit the units because, well, you know what you're getting right here, just volts. Times L, that's length, and it's 8 meters, not 4, because it goes both ways, divided by, okay, and this is really important. If you have copper, that's the value, if you have aluminum wire, that's the value, and I had copper for my purposes, thankfully, because I would have to compensate even more if it was an aluminum. And well, the lower the value, the poorer the conductivity, okay, so and well, 58 over here times our voltage, 12 times, and S here is a diameter in millimeters square. So for my purpose I used 1 millimeter square wire because I wanted to make it as thin as possible, and well, if I use a thicker wire I wouldn't have as much issues here, so 1. I will omit the times 100%, and we can move this 12 volts over here, so we will get a delta U equals 2 times 4 times 8 times 12 divided by 58 times 12 times 1. You can remove those 12s. The 1 here doesn't matter. So you have 64 over 58, and that is about 1.1 volts. So here you have it, 1.1 volts drop over the course of the lead. And I did my measurements, and I think I had they used a bit thicker wire, because when I measured, and how you can measure this, so you just know, you can measure here and check the difference, but also you can measure over here, between here and here, the voltage, and you will have the half of the drop. And for me it was 0.48 volts. So well, that's really not that bad, especially if as we were counting just now, it should be something like 0.55. So we will use this value, this one, because well, you can always adjust your circuit a bit more to the reality, but we'll keep this in theory. So let's move on with this value. So you have 1.1 drop, and what you can do with that is just use the power supply to adjust it so it will run more. It will give out more volts. So for our purposes, I just set it to 13 volts, and we will keep that. And so we have 13 volts DC, 13 volts power supply. And what's important and what you should know is that when you count these things, well, basically, I'm not sure if you are able to see this. Focus, right? Almost. Yeah. Okay. So we have 2.5 centimeters parts that are basically. So we are connecting something like. Okay, over wire. Here's our drop, so we will have 12 volts here, and then what it does, plus minus, and you have something like this. One LED, then second one, then the resistor, it's 150 ohms. Then the third LED. Well, it doesn't matter You can switch those around, but I'm just drawing it like it is on the circuit, and it goes back. So and basically you have the same things over and over again. So you have again and again. I won't draw the arrows, you know what I mean, and that's times 198, because this is 1.5 centimeters. So, and you have 2 here and 200 the rest. So that's pretty obvious. And you have you have something like this. So this is connected here to the plus, and this goes back to the minus. And so you have all those segments in parallel, and you have to keep that in mind, because it's not really that simple, especially if you are dealing with cheap LED strip like that. So you have all those segments in parallel, and the last one will have also a voltage drop, because the board is not really that thick, and it's even thinner than my own 1mm square wire. So I measured, and the last one right here, I measured the voltage here, because as you can see it goes down, 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 and down, and between those I had I think if I had 12 volts here, there was something like 9.7 volts. It still was shining, but not that bright. And how can you mitigate this? Let's take this part and let it called simply this part of the circuit. Let's call it a segment, something like this. Let's make it a segment. Okay, so it will be easy to draw. So you have your we will simplify this. You see 12 volts. Let's pretend that you are already after the drop. You have your plus, your minus, and it gives out all those the current for the LED segments. Times 3. LEDs times 3, and LEDs times 3. Okay, and this is really shoddy, and well, you get the idea, right? So all of those are in parallel, and after you measure this one, after all the 5 meters in length, you have 9.8. So 9.7. So 2.3 drop on the length of 5 meters, and well, somehow we have to compensate for this. And because my LED strip was going around the frame, so it was easier for me, I simply took a piece of thick wire and soldered it here, made a connection, and also soldered it here. So even though you have a connection over here, this has a lower resistance, and you will be able to power those LEDs. And this was really good, because suddenly on this side you have 12 volts, on the first one had a 12 volts, and somewhere in the middle, the drop, somewhere in the middle, right in the middle of the circuit, so after 2.5 meters, there was still a drop, because I was, as this was a frame, 5 meter frame, I wasn't able to connect another wire. I mean, I could, but I had to guide it through the frame and so on. I didn't do that. And somewhere in the middle, as you had a 2.3 volt drop, so divided it by 2, that was 1.15 volt drop. So from 12 volts, that was 10.85 volts. And even though this is not really that bad, you don't have the maximum brightness for what you are, well, what you paid for. Well, I was expecting this LED strip to be kind of working really well, but it said on the packaging that you can have maximal length of the strip should be 5 meters, so I was expecting they will compensate for this, but they didn't. And the problem here is that you have 10.85. So I decided that, I will overdrive those LEDs. The first one and the last one, so they will, the drop will be well, not that big, and everything will compensate. Because if you take a look at any data sheet, and you will see on the data sheet there will be a chart, so luminescence and milliamps, and what you are usually seeing is almost straight line, and this is the perfect point that the nominal current, and for those LEDs is 20 milliamps. I will go to explaining how I get to this, and for the luminescence you have, right, so it's almost at the max. And it suddenly drops here because you will have the maximal current here, and at the maximal current there will be a lot of heat dissipation and a lot of issues. This will reduce the lifetime of the LED and so on, but well, I don't really mind. These are the cheapest ones, something like, I think, $8. Well, don't care, sorry, 8, maybe something more. Something like 10 maybe. How did I get to the point that the LED runs at 20 milliamps? Well, I started with counting, and for 5 meters I had 200 of those little circuits, because 2.5 centimeters for each one, so 200 times the current that goes through each one, so because they are in parallel. And how can you count the current at the nominal voltage? You have your one LED, second one LED, your resistor, 150 ohms, so 3 LEDs, right? 200 times this. So if you check with your meter or check on the data sheets online and so on, you will get to the point that usually they are driven at 3 volts, and that this is their voltage drop. So we have 3 volts, 3 volts, 3 volts, and we don't know what's going on here. And this is the only current limiting element in the circuit, and this is important because we want to limit the current so it won't be overrun. And okay, so we don't know how much this, but here should be a drop of 3 volts, because in total you will get 12 volts, right? And that's pretty easy. And to get the current that's going through this resistor, it's as simple as that. It's R equals the V over I, V for Western, right? We have U here as a symbol for the voltage, and you can change this formula to I equals V over R. So the current will be voltage, 3 volts, over 150 amps. Let me just show you that. 150. This is in amps, so 20 millivolts. Perfect. Milliamps. So 200 times 20 milliamps also will tell you that we already got the current. So 4 amps. Yeah, everything goes together. And I decided I will overdrive them. So I will get best brightness for my back, and so I started to driving them. We have a 1.1 drop on the at the beginning, so I decided that I will drive the DC at the beginning at 14.1 volts, something like that. I adjusted it to make sure the current after the voltage after the wires. So over here we have something like 13 volts, more or less. Of course, this will change. You have again go with the formula, check the voltage drop and so on, because it will. Well, hold on. It shouldn't change because we are removing those two, so it even shouldn't change for this wire thickness and for this amp. So that's pretty good. And 13 volts over here. We are overdriving some of the segments. Ladies, because we want to have, this is plus, this is minus, because we want to have, okay, so this goes back to here again. This will go back to here, and so on. So the last one, even well, not the last one, because we already discussed it, that we will connect the first one and the last one. So we will have 13 volts at the beginning and at the end of the circuit, times 3. This is the middle one. So, well, I will just write the minus, plus, minus, plus. You get the idea. And we were already connecting, even though it went through the whole circuit. We already connected the minus right here again, and the plus went straight here. So we have 13 volts here, 13 volts here. In the middle we have the drop, the 1.15 volt drop. So even though there is a drop, we still have here 11.85 volts, and this is pretty good, because let me just count the current that goes here and also here for the 11.85, because for now we're interested in the brightness. I will get back to the overdriven LEDs in a moment. So you have your middle segment. This is the middle one with 3 LEDs. You always have your 3 volts drop. That's pretty obvious. And now you know that here it drops 2.85 volts. And 2.85 volts, the current is 2.85 divided by 150, 19 milliamps. That's really good. But on our chart, you are just behind the nominal current. That's really good for the luminescence. And this is well, we're golden here in the middle of the circuit, and for the beginning of the circuit and the end. So the beginning and the end, we have our LEDs. Well, I'm drawing even sloppier LEDs than at the beginning. Sorry about it, but you get the idea. 3 volts, 3 volts, 3 volts, 4 volts, because 13 and 4 volts divided by 150 is 26.7, right? Milliamps. So I is 26.7 milliamps. And the fact is that the brightness won't be that much different. What I should do now is look into the datasheet of this LED. This LED packaging is 3528, and this is basically the size. This is 35. Let's show you that. Maybe you'll get a focus here. Okay, so the width is 35 and the length, and this one is 28. So 3.5 millimeters by 2.8 millimeters. So I should look in the datasheet. I wasn't able to find this particular LEDs, but I was looking around for warm LEDs with 3 volts, 20 milliamps nominal, and what I found out, there was a different LEDs made, but well, you didn't have single LEDs that said, for example, you cannot drive those, the maximal current is 22 or something like that. The worst scenario was 25, and even though I can live with that, I can live with overdriving the LEDs at rate 1.7 milliamps. I mean, that's not the worst scenario in the world. And if you want, you can a bit decrease the 13 volts to something like 12.8, and this current will drop. Keep that in mind. I just wanted to get the best brightness I can get. And the thing is, I measured the circuit before doing all of those calculations, before compensating for the drop at the LED strip. So I put an amp meter between my DC12 and I think, yeah, and my LED strip, 5 meters. Okay, I put an amp meter here. So after the wire, even though I compensated for the wire, I had here 12 volts. I received here a measurement of 1.7 amps only, and this, well, I got a bit angry at the guys that made this, because, well, they promise 4 amps, and the more amperage, the brighter they get. So after compensating it, so connecting all of this together again, rising the voltage to 13 volts. So okay, so let's call it 13. So after that, I had steady on 3.4 amps. This is still less than promised 4 amps, but, well, there is also a voltage drop and so on. And I didn't want to overdo this. And as for the wire, keep in mind the thinner wire you'll get to connect those LEDs. Well, basically you are creating a heater in your home. So if you consider this wire at 3.4 amps times our drop, so 1.1 volts, gives us 3.4 times 1.1 volts drop in total, 3.74 watt heater in the room, and that's just the wire, not the LEDs. This is the wattage you are wasting away, and you could use this and so on. All the drop on the current could be also caused by the drop on the leads and so on. I didn't wanted to go into that even more because, well, that's not really the point. I got the bright LEDs. I want to thank the European Union and their import laws for the fact that my camera turned off right at the moment. I wanted to thank you for viewing, and I hope this was informative for you, and you will be able to connect your LED strip and shine as bright as day.